So as I said, we probably don't have time to finish this chapter, but we will finish about halfway done of this chapter. Okay, this chapter actually include like autoencoder and the GAN. Okay, we should be able to finish autoencoder. Okay, so autoencoders are artificial neural network capable of learning dense representations of the input data. Okay, this dense representation is called latent representation or coding. Okay, so without supervision. So this is like you can say it's a self-supervised learning. Okay, because the training set is unlabeled because like I mean, why we don't need a label, I'll explain shortly, okay? So these codings typically have a much lower dimensionality than the input data. This makes the autoencoder useful for dimensionality reduction, okay? We will talk about this dimensionality reduction, later. But actually, it was covered in the chapter 8 of the textbook, but obviously we didn't cover chapter 8. If you read the textbook yourself, then dimensionality reduction is, is discussed in great detail in chapter 8. Okay, so especially for visualization purposes. So autoencoders also act as feature detectors. They can be used for unsupervised pre-training of deep neural networks. I mean, we talk about unsupervised pre-training, but at that time, I told you guys that, this is normally done by using the autoencoder, but at that time, because we didn't, we haven't touched the autoencoder material yet. So I can only tell you this unsupervised pre-training, but this term, but really like we didn't have a good example for that. So here, okay, in this chapter, we are going to I'm going to show you an example of that. So lastly, some autoencoders are generative models. What does it mean by generative model? Okay, they are capable of randomly generating new data that looks very similar to the training data. So this is very interesting. This is very interesting. For example, you could train autoencoder on pictures of faces, and it will then be able to generate new faces that looks, just like a real face. However, the generated images are usually fuzzy and not entirely realistic. Okay, if it's generated by autoencoder, yes, it's not going to be high quality. If you want the data generated by model to be high quality, then, well, you have to use GAN. Okay. So in contrast, face generated by generative adversarial network, okay, are so convincing. Okay, it is hard to believe that the people they represent do not exist. Okay, you can judge by yourself. Okay. So let me show you. An example. Shoot. Sorry, I don't have internet connection. Yeah. Okay. So this is like a, oops, sorry. Oops, sorry. I need to reduce this. Eh? What happens? So this is not real person. This is generated by the GAN. Okay? So I can actually reload this page to show you different person. Okay, but of course those persons are not real. They are generated by the same model. It looks like a real photo, right? Okay, so you can, this is a website called thispersondoesnotexist.com. Okay, and there's another, you know Airbnb, right? You know Airbnb, right? Sorry, not this. I hate the, yeah, the Airbnb. The Airbnb, so I can actually use, I mean, there's a model, the GAN model that is used to generate the so this is like a fake Airbnb page. Okay, everything, including the picture, including the description. Actually, this guy and this top Lavino apartment 2. Okay, everything on this page is generated by the GAN model. Okay, I can actually, you know, again, refresh this this page to show you, you know, so many different, you know, fake Airbnb rental. Okay, and this is a website. This website is called thisrentaldoesnotexist.com. Okay, so you can see like this. You see a potential of committing crime, right? Yeah. I'm not telling you how to commit crime, okay? I'm just telling you the potential. Okay. So anyway, oops. So the face was actually generated by a model called StyleGAN. Okay, I mean, a more sophisticated GAN model was used to generate this rental does not exist.com. Okay, so GAN are now widely used. Okay, for super resolution, like to generate the image. I mean, with even higher resolution than the original one. Okay, and colorization. So you may have like a black and white photo, and you can use GAN to generate like a colored photo that looks like real, and the powerful image editing. Okay, replacing photo bumpers with realistic background. Do you know what photo bumper is? You know, like when you take a photo, I mean, they are maybe like they are passengers that pass through the background, right? And you hate those passengers, right? Okay, because those passengers may block some, I mean, like sightseeing locations you want to take the photo with, right? So those things are called are called photo bumper. Okay, photo bumper. Those like obstacle. Okay, that you don't want to be in your photo. Okay, basically are called photo bumpers. So you can remove the photo bumper, but once you remove that photo bumper, you will have some blank in your photo, right? So the GAN is able to fill those blank with realistic background. Okay? So turning a simple sketch into a realistic image, predicting the next frame in a video. Okay, augmenting data set. So you may even use like a GAN to generate a lot of photos, and then use that to train your model. That's possible. Okay, so this is, the GAN has many sophisticated applications. Okay, identifying weaknesses in other models and strengthen them. Okay, so all this, of course, they can be done by different GAN. I'm not saying that one GAN can do them all. Okay, okay, so what's the difference? Okay, between autoencoder and the GANs? Okay, autoencoder and GANs are both unsupervised learning. Okay, they both learn dense representations. Okay, they can both be used as generative models. Okay, keep in mind. Okay, GAN, most of the purpose of the GAN, most of the application of the GAN is generative. Is for generative model. Okay, but for autoencoder, most of the application for autoencoder are not necessarily generative model, but autoencoder can also be used as a generative model. Okay, so they have many similar applications, but they work very differently. Okay, autoencoders simply learn to copy their input to the output. So this is very interesting, right? You get the input and you copy the input to the output. So how come you can learn something? Okay, but okay, this sounds like a trivial task, but okay, we can constrain the network in various ways to make this copy process difficult. Because we make this copy process difficult, okay, the model is able to learn the internal representation. Okay, so I will explain in more detail. But basically, okay, for autoencoder, okay, we have encoder and a decoder. Encoder convert the input to coding, and decoder convert the coding back to the, as close to the input. Okay, but so the purpose of autoencoder, okay, is to copy input to the output. Yes, but of course the application of autoencoder is not copy the input to the output. Otherwise, it's, why do you need autoencoder, right? It's like when you are able to learn the dense representation, you have a lot of applications that you can do with the autoencoder. Okay, so that's like autoencoder. Okay, this constraint prevents the autoencoder from trivially copy the input directly to the output, so which forces the autoencoder to learn efficient ways to represent the data. Okay, so the coding are byproduct of autoencoder learning to the identity function, because we want to copy the input to the output. So this is pretty much an identity function, but we intentionally make it difficult. So we are able to learn the coding as a byproduct. Okay, under this difficult constraint. Okay, but on the other hand, GAN is very interesting. Even though in this chapter, in this class, we probably, as I said, we probably don't have time to finish this GAN in our lecture. But I would like to at least talk about the basic concept. Okay, GAN are composed of two neural networks. The first one is called generator. The second one is called discriminator. So this generator will try to generate fake stuff, and the discriminator will try to identify if this input is real or fake. Okay, so they kind of compete each other. You can imagine one is like bad people. Well, actually, model is not bad, but you can imagine you can sort of like compare the generator as like a bad people. Okay, trying to fake, for example, create like a fake bill. Okay. 做假钱呐 okay, fake bill. And you can try to compare the discriminator as like police. The police is trying to identify, okay, if this bill is fake or real. Okay, so, we call it, in Chinese, we have a saying like, 道高一尺，魔高一丈, right? So these two models are competing each other, and, So the generator will become better in generating the picture, okay, to make it as realistic as possible. Because the purpose is to what should I say, like to cheat the discriminator, right? And the discriminator is going to become better and better in terms of, it's trying to, tell if the input is a fake or not. Okay, so these two models, when they are getting better and better, eventually, we are able to generate like a photorealistic images. Okay, of course by the generator. Okay, so this concept, okay, is called adversarial learning, adversarial training. Okay, adversarial training. This means training competing neural networks. Okay, you have two neural networks competing each other. This concept, okay, is considered widely as one of the most important ideas in recent years. In 2016, remember I keep telling you, Yang LeChong is really genius. Okay, so in 2016, Yang LeChong said that it was the most interesting idea in the last 10 years in machine learning. Okay, so you can see like why. Okay, the GAN has so many different applications. It's a pity that we don't have enough time to cover GAN, but I highly suggest, even though we are not going to talk about it, and I don't plan to have a question assigned for GAN in final exam, but I highly recommend you guys read this by yourself. Okay, read this second half of the chapter by yourself. Okay. So outline of this chapter. Okay, in this chapter we will start by exploring how autoencoders work and how to use them for dimensionality reduction, feature extraction, unsupervised pre-training, or generative models. Okay, so once we cover generative model, this application for autoencoder, it will naturally lead us to GAN, but I think at this point we will stop. Okay, we don't have time to finish the other part. Okay, so in the GAN part, we can build a simple GAN to generate fake images, but the training is often quite difficult. So a lot of context in GAN is contributing to how we can deal with how we can handle these difficulties. Okay, such as like we have a list of techniques to deal with like the model training in GAN. Okay, the GAN is very sensitive in training. Okay, just a little bit of change can impact the result a lot. Okay, so anyway, I really suggest you guys like to take a look at the GAN. In the textbook. Okay, so we still have like 20 minutes. So first, okay, let me give you this example. Okay, so we have like these two number sequences: 40, 27, 25, 36, 81, 57, 10, 73, 19, 68. Another one is 50, 48, 46, 44, 42, 40, 38, 36, 34, 32, 30, and so on. Let me ask you, which sequence is easier to memorize? The lower one? Why? Yeah, because it has a pattern, right? You can find the pattern in this sequence. If there's no pattern, which one is more difficult to memorize? The lower one. Why? The longer sequence is more difficult to memorize because if there's no pattern, you have to memorize them like very hard in order to memorize the whole thing, right? But once you understand the pattern, the lower one suddenly becomes so easy, even though it is longer, right? This sequence is longer, right? So the coding that we are talking about, or latent representation, is the pattern. Okay, basically, okay, you can imagine, okay, once you understand a certain pattern, it becomes much easier to memorize a sequence, right? Okay, so the same thing can be said for example, English vocabulary, right? Like in junior high school, when, well, actually, you guys learn English first from elementary, now? Okay. So in elementary school, I mean, when you first learn English, you probably just have to memorize every single word, right? But now, I mean, once you have learned English for a couple of years, maybe some teacher will start telling you, okay, you have like the root, right? 字根, and you have like a prefix and a postfix, 字首字尾, right? So certain root represents certain meaning, certain prefix, certain postfix means certain thing, right? So those rules will help you to memorize the meaning of the English words much easier, right? Okay, so basically all these the rules that you can observe from long sequence help you to be able to memorize the sequence much better. So that basically the rules are the latent representation or coding. Okay? So, okay, the relationship between memory, perception, and the pattern matching was famously studied by this Chase and Simon in early 1970. So this is done by this psychiatrist. Okay, so they observed that expert chess players were able to memorize position of all pieces in a game by looking at the board for 5 seconds. With just 5 seconds, they can, basically reproduce the whole setting of the game. Okay, so this is amazing. Okay, here the chess we are talking about is the Western chess, right? Like a 西洋棋. Okay, but those experts are not really so special in terms of memory. Because if you do not put those pieces, from the realistic position, some chess pieces can only appear at some places, right? So if you randomly put them in arbitrary position, those experts cannot memorize the game. Easily. Okay, this same similar phenomenon can be observed by in a professional Go player. Okay, because I play Go, I don't play chess. Okay, unfortunately. Okay, so in professional Go player. Okay, well, for example, a professional Go player on average play like more than 100 games per year, okay? And they pretty much play game since their childhood, okay? From their childhood. So up to like 50, 60 years old. So think about this, okay? Let's just say they play game for 50 years. So assume each year they play only 100 games. So we are talking about how many? 5,000 games, right? 5,000 games. And pretty much you can ask any professional Go player if they can reproduce every single move of any game they have played in their career. They can reproduce we call that 复盘. Okay, the professional Go player is able to do that. Okay, for every single game, these 5,000 games. Okay, why? Because they memorize their steps by the rationale behind those plays. Okay, so they are able to memorize so many games. So each game, you have like hundreds of move. Okay, so this is crazy, So, but if you just randomly put like pieces, on the board, nobody can do that, can memorize that. Okay, not even like a professional Go player or like a chess player. Okay, so this pattern is an important concept. Okay, it's an important concept. Okay, so just like a chess player, okay, in the memory experiment, okay, an autoencoder looks at the input, converts the inputs to efficient latent representation, and then spits out something that, okay, looks very close to the input. Okay, an autoencoder is always composed of two parts. An encoder, okay, which converts input to latent representation, or we can call coding. Okay, that's why. Okay, this part is called encoder. Okay, or another way to call it is called recognition network. The other part is called decoder because we convert the coding back to the input. Okay, so it's called decoder. Okay, another way to call it is called generative network. Okay, which converts the internal representation or coding to the output, which is as close to the input as possible. So this looks like this. Okay, you have a chess. This guy, well, actually this is not a chess player, but you get the idea. Okay, so he is able to observe the pattern, and he's able to reproduce the pattern like as close as the input as possible. Okay, so this is another example. You can see this is our encoder. This is our decoder. Okay, this is the real autoencoder. So we have 3 input, and we have 3 output. And these 3 input, okay, these 3 output is hopefully as close to these 3 input. Okay, that's the purpose of this autoencoder. For any autoencoder, this is the purpose. The output is as close to the input as possible. Okay, so as you can see, autoencoder typically has the same architecture as a MLP, right? We have learned MLP in chapter 10. Okay, except that the number of neurons in the output layer, okay, must be equal to the number of input. This is not required in MLP, right? This is not required. The input neuron, number of input neuron has to be the same as number of output neuron. This is not necessarily the case. Well, actually, this is most likely not the case in MLP, but this is always the case in autoencoder. Okay, so in this example, there's just one hidden layer composed of 2 neurons. This is what we call coding layer. Coding layer. Okay, and so one output layer composed of 3 neurons. We call that decoder. So output are often called reconstructions, okay, because the autoencoder tries to reconstruct the input, okay, and the cost function contains a reconstruction loss. This reconstruction loss will penalize the output if the output is far away from input, okay. So basically, if it's the same as the output is the same as input, then the risk reconstruction loss is going to be 0. Okay, it's minimized. Okay, so because the internal representation has a lower dimensionality than the input data, okay, the autoencoder is said to be under-complete. So this one, because our input, we have 3 inputs, right? So these 3 inputs obviously is 3-dimensional, right? But once these 3 inputs are fed to this layer, remember I told you this is a coding layer, right? This coding layer, because we only have, this coding layer is only able to memorize 2 numbers, right? Each neuron can only store 1 number, right? So from 3D to 2-dimensional. From 2-dimensional, we have to go back to 3-dimensional. So think about this. Okay, because this dimension, the coding dimension is lower than the input dimension. So this is called under-complete autoencoder. And another thing is that you can imagine, okay, so this is obviously a constraint, right? We are trying to put a constraint to make it difficult to copy the input to output, because, well, if the input is 3-dimension and here we only have 2-dimension, we have to find some efficient way to store the input. Otherwise, well, you really, how can you just use 2 numbers to store 3-dimensional information? This is difficult, right? So if you train this model, okay, then yeah, I mean, this coding is going to be a more efficient representation of the input, okay? So an under-complete autoencoder cannot trivially copy its input to the coding because, well, the dimension is not enough, okay? Yet it must find a way to output a copy of its input. So it is forced to learn the most important features in the input data. Okay, if it has to give up certain information from the input, we want it to give up as little as possible, So it only drop the unimportant information. Okay. So let's see how to implement a very simple under-complete autoencoder for dimensionality reduction. So, by the way, I mean, what is dimensionality reduction? Okay, if autoencoder uses only linear activation and the cost function is the mean square error (MSE), then it can be shown that it ends up performing PCA. Okay, PCA is the famous method to perform dimensionality reduction. So PCA identifies the axis that accounts for the largest amount of variance in the training set. Okay, so for example, so for given points like these blue points, okay, you can obviously see that this axis, has the largest variance, right? Has largest variance, this axis. Okay, here, of course, I am assuming these points are 2-dimensional points. Okay, so if you want to reduce these 2-dimensional points into 1 dimension, then you are going to take this dimension. What do I mean by take this 1 dimension? I mean, okay, so this is going to be your, what should I say, like your space. And all these points will be projected all these points will be projected to this, this line. Okay? So that, okay, you can see, once these points are projected to this line, this largest variance will be preserved, right? Because this axis represents the largest variance, right? And because all these points are projected to this line, so the variance on this dimension is going to be dropped, right? But because compared with this variance, the variance on this dimension is much smaller, right? So we consider this variance as unimportant, okay, because they are much smaller. Okay, but so the PCA, okay, if you reduce these two-dimensional points into one dimension, then the point projected on this line will be what the result you get. But if you say, oh, we use a PCA to get like one dimension, and then we use PCA to get a second dimension, then the second dimension will be, perpendicular, will be orthogonal to this direction. Okay, it's going to be this one. Because once you get rid of the variance of this dimension, then the resulting variance will be on this dimension, right? Okay, just want you to understand this. Okay, so if PCA finds a 2D representation, you will also find the second axis orthogonal to the first one that accounts for the largest amount of remaining variance. Okay, well, I think I'm out of time, so yeah, I will stop here today. Okay, so next time we will start from like implementing this autoencoder for PCA. Okay? Any question? If no question, let me remind you once again. Okay, next week will be the final lecture. Okay, the week after next will be the final exam. Okay, and the sample final exam has already been uploaded to EE class. And 3 weeks from now is going to be the presentation of the term project. Okay, and what else? Yeah, there will be pizza offered. Okay, starting from 12:30 for the presentation. Okay, session, and also for the final exam, you are allowed to bring in 1 page cheat sheet, just 1 page. Okay, whether or not it's both sides or just one side, it's up to you. I will not check what you wrote on that cheat sheet. Okay, but please don't bring a book. Okay, that's reasonable, right? Okay, so any other question? Then I'll see you guys next week. Okay? Okay. 可以吗? Okay. So today is our last lecture. Okay. The next week is going to be the final exam, and the week after next is going to be your term project presentation. Okay, just want you guys to be aware of that. And well, not too many students showed up. Okay, but that's fine. Okay, so we talked about the autoencoder last week, right? So today we are going to finish the autoencoder part. So we have about 60 slides. Okay, so I'm going to be, a little bit, have to be a little bit quick on today's lecture. Okay, so we talk about the concept of PCA, right? And if your autoencoder, the input dimension, is is higher than the coding, and you are using the linear, okay, it's going to be something like if the input is 3-dimension and the coding is 2-dimension, okay, and you are using MSE as your, you know, like a cost function, then this autoencoder, after you train it, is going to work as a PCA, okay, in the sense that the input is 3-dimension and the output here, I'm not talking about the output in the real output, I'm talking about the coding. The coding is going to be, you know, 2-dimensional, okay? So this part, the encoder will perform the dimensionality reduction in our PCA for you, okay? So the construction, okay, the program, okay, to design autoencoder is like this, okay? So you can see the encoder is very simple, okay? It's just a sequential API, and then we specify just one layer, okay? The input shape is 3, and we have 2 neurons. Decoder is, again, it's only one layer, okay? The input shape is 2, and the output is 3, okay? And it's, you know, we have 3 neurons, pretty much, okay? And you can see that, okay, after we create encoder and decoder separately, we put them together to form our autoencoder model, okay? And as I said, if you specify the loss to be MSE, oh, by the way, if you do not specify, for example, like your activation function, okay, using the linear function, okay, only, then, and the loss function to be MSE, then, you know, you train this model, eventually it's going to work. The encoder part is going to work as like a PCA for you, okay? Optimizer is a stochastic gradient descent. This part is the, you know, not much to talk about, okay? So we already talked about this thing, and so you can train this model. And the one thing interesting you can see is that, okay, here, obviously, you are training this model for 20 epoch. And this is your training data set. And this is your label. And you can see that the training data set, the input is the same as the label. Okay, remember, in the autoencoder, we want to make sure the input is, the output is as close as the input, right? So that is why, okay, well, I mean, we use the you know, input as our label, okay? So once we finish training, okay, we can use the encoder, as I said, as a PCA, okay? We feed in the X-trend, okay, which is a 3-dimensional data set, and we use the predict from the encoder to produce the codings. And these codings, obviously, is going to be 2-dimensional because we only have like a 2 number. Okay, there are only 2 neurons in the coding layer. So it's going to work something like this. So these are like a point on the 3-dimensional space, in the 3-dimensional space, and it's going to find the a plane, okay, with the smallest, you know, loss of the projection, and then project all these points to this 2-dimensional space, and it's going to become something like this. Okay, another way to say this is like, okay, you want to preserve the data set that has the largest variance. I mean, which obviously is maybe somewhere along this line. Another, once you get rid of this variance, you can see most of this point, this direction also has a large variance, right? And then these 2 vectors somehow span, you know, a plane, which will be like this plane. And then you use this plane and have all these points project to this plane, and it's going to be something like this. Okay, that's the basic concept of the PCA. And obviously, okay, the autoencoder is just like a self-supervised learning, okay, because or unsupervised learning, because you don't need to label the data set. I mean, basically the output, label is just the input, okay. So this is obviously a desired property, because like we can make use of this. I mean, in several applications, as I will talk about this today. Okay, so just like our neural network, okay, autoencoder can have multiple hidden layers, because the previous one we talked about, okay, we only have one layer for the encoder and one layer for the decoder, but this is not necessarily the case. Okay, we could have a stacked autoencoder. Okay, when I say stacked autoencoder, I'm talking about like the autoencoder that has like multiple layers in the encoder as well as the decoder. Okay, and remember that, okay, a stacked autoencoder normally looks like a sandwich, in the sense that it is symmetrical. Okay, it is symmetrical with respect to the coding layer. Okay, let me show you an example. Like this. Because the input layer, the size of the input layer has to be the same as the size of output layer, right? Because obviously you need to reconstruct the input, right, in the output layer. So the dimension of the output layer has to be the same as the input layer. This goes without saying, right? But the stacked autoencoder actually goes like much more beyond that. Okay, you can see that. Okay, this hidden layer 1 has the same shape of the hidden layer 3. Okay, and hidden layer 2 in this particular example happen to be the coding. Okay, and you can see this architecture pretty much is symmetrical with respect to this coding layer, right? So this is not just an example. Okay, any stacked autoencoder look like this. Okay, so, but of course, like different layers may have different number of neurons. That's obviously, not fixed. But you can see that. Okay, for this particular example, okay, we are trying to use the fashion MNIST as an example. So that's why you see the input layer has 784 units, because it's 28 by 28. Okay, and output we are trying to reconstruct that fashion MNIST small picture. So it's also like 28 by 28. Okay, and the internal part. Okay, this type of autoencoder is called undercomplete autoencoder, in the sense that the coding layer dimension is lower than the input layer. Okay, in this case, because obviously the coding layer, here we only have 30 units. Okay, so this dimension is much lower than the input layer, right? So this is what we call like undercomplete autoencoder. There are some other cases that we have like a wider coding layer than the input layer. It's possible. It's possible. In that case, we call such an autoencoder over-complete autoencoder. This is just a naming. Okay, just want to give you an idea what that is. Okay, and then if you want to implement such a stacked autoencoder using Keras, it's very simple. Okay, you can see, again, we use a sequential API. As I said, we use like a fashion MIST, so the input layer is just like we flatten the 28 by 28 like pictures, and then okay, we have 100 neurons, okay? And one thing interesting is that we use zero, okay? I mean, obviously, zero can also be used for autoencoder, okay? Just like any other neural network, okay? And also, if you still remember, if you use zero, you have to use the zero throughout the whole model. So here, okay, the coding layer, okay, 30 neuron, we also use zero. Okay, so this part is the encoder. Okay, for the decoder, okay, we take the input, I mean, from the coding layer, which is 30, right? And we expand it to 100 neurons, and using zero again. And then, okay, here, okay, we are supposed to, go back to 28 by 28. Okay, so we have 28 times 28, and the activation function is sigma. This is very special. Okay, and we reshape this 28 times 28 into 28 by 28. Okay, into two-dimensional, because this is one dimension. We want to, because eventually it's going to be treated as a picture, so it has to be two-dimensional. Okay, and I want to make. The reason we could use sigmoid is because, okay, obviously the sigmoid output, okay, the output value in the range of 0 and 1, right? It's a sigmoid, right? Okay, so that means this input, okay, remember, like it's a grayscale picture, right? The facial MIST is grayscale picture, right? So each point, okay, has an intensity, right? It doesn't have like 3 channels, okay? It's not like a colored image. So each pixel has an intensity from 0 to 255, right? So you can normalize that value into, the value between 0 to 1. Okay, so you first has to normalize that into, each pixel has to be normalized into the range between 0 and 1 before you feed it into this autoencoder, okay? And then, okay, because we use sigmoid, so you can see that here, okay, when we put the encoder and decoder together to make this stack autoencoder. And one thing interesting, okay, you can see when we compile this stack autoencoder, okay, what is the loss function that we use? We use binary cross entropy. Okay, the optimizer is not much to talk about, but the loss function we use binary cross entropy. If you still recall, okay, you remember binary cross entropy is used for binary classification. Remember? Right? We have like if you use binary cross entropy, that means like this model is used to for the binary classification. Okay, and the binary classification, each neuron will output a value between 0 to 1, right? Okay, that normally we will consider that as like the probability for the positive class, right? Right? That's binary classification, right? But now, we actually treat this one, the model, as 784 binary classifications. Okay, so each output is considered as one separate classification. But of course, we are not doing a classification. We are just trying to treat it as this many classifications. Okay, so that's why we use binary cross entropy. And then we can train it with 10 epoch okay, again, we use the same data set as the input and the label, okay, as I already mentioned. And we use, again, the same thing as the validation set and the label for the validation set, okay? So well, we train this one for 10 epoch, and then, okay, then we can get like a stack autoencoder for the fashion MNIST, okay? So this part I think I already talked about, okay? Yeah. So you can visualize, the reconstruction of this stack autoencoder, okay? Here we just try to, plot the image, okay, of the original input as well as the reconstructed one, okay? And we try to show that, how good the reconstruction is, okay, using this stacked autoencoder. So this is just the code to output the picture. So I was, if you are interested, I mean, you can check out the detail, but basically it's just to draw those the pictures. Okay, so the top lines are what we fed into the autoencoder. Okay, and the lower row shows the reconstruction. Okay, and you can see from, if you look afar, okay, you can see they look similar, right? Although you don't feel like the lower row, okay, I mean the picture in the lower row have good quality, okay, probably you don't feel like that, but at least they are similar, right? I mean, if you prefer to have to have the autoencoder to reconstruct, I mean, even higher quality picture, okay, there are several ways to do that. First, obviously, okay, training only for 10 epoch is probably too short. You may want to train it even, a little bit longer. Second, okay, this autoencoder, okay, even though you can see this model, okay, is pretty much the smallest stack autoencoder you could possibly get, right? Okay, we only have like not including the coding layer, we have only 2 layers for the encoder and another 2 layers for the decoder. Okay, if you want the autoencoder to be able to reconstruct whatever input better, okay, one way to do it is to increase the complexity of the model, just like any neural network. Okay, if you want the neural network to be able to do more sophisticated work, okay, you may want to consider increase the complexity of the model. Same thing goes for the autoencoder. This one is a pretty simple model, okay. If you talk about like a stack autoencoder, okay. So obviously it doesn't perform that well, okay. That's another issue, okay. You can see, for example, like if you really look at this reconstructed T-shirt, you will feel like okay, the length of the 2 sleeves seem to be a little bit different, right? This part is longer than this one, right? Okay, so yeah, but you get the idea, okay? So this reconstruction, is a reconstruction of the input, okay? So, as I said, if you make the autoencoder to more powerful, it is able to better reconstruct the input. But you also need to be careful not to make autoencoder too powerful, because if you make the autoencoder too powerful, it will manage to make perfect reconstruction without having learned any useful patterns. in the data. Okay, so because, okay, the reason we construct the autoencoder is really not to reconstruct the input, right? Think about this. Okay, here, okay, I show you, okay, this is a reconstruction of the input. Yes, this is just to show you an idea, okay, of this autoencoder. But I just show you a concept. But in reality, I mean, I will not use this as an application, right? Because, well, if I want to reconstruct input, why do I need to do that? I already have the input, right? I can just use the input directly, right? Why do I need to reconstruct the input when you already have the input, right? So this is not the real application of the autoencoder, okay? The real application of the autoencoder, okay, one of the applications that I just mentioned is PCA, dimensionality reduction, okay, or some other applications that I'm going to mention later, okay? But for those applications to work, okay, you probably do not want the autoencoder to be too powerful, okay, to easily reconstruct the input, okay, because, you know, just like, you know, now, okay, if I give you a list of a number, remember I gave you an example, right? A list of numbers. If those numbers, okay, if I tell you, okay, you can only use very simple rules to memorize those, the sequence of numbers, then you have to, you know, you are forced to find a better way to represent those numbers, right? Because you only have a very small space to represent those numbers. But if I tell you, okay, I don't care how much space you use, then when you see this list of numbers, you just copy them, right? You don't learn anything, right? Okay, if I do not, you know, kind of like, you know, enforce certain restrictions, then this reconstruction, through this reconstruction, the model is not going to learn anything, any pattern, okay? So this is, I mean, but it's a pattern that the autoencoder picked up that is going to be useful in the real application, okay? So we have trained a stack autoencoder. We can use it to reduce the dataset dimensionality. Okay, this is of course one of the possible applications, but yeah, for visualization, this does not give great results compared to other dimensionality reduction algorithms. Why? Because, okay, think about this. The original dimension is 784. Okay, so that's a lot of dimension. When it go down to the coding, it's 30 dimension. Okay, compared with the input, yeah, it's really reduced the dimension, the size of the dimension by a lot, more than 20 times, right? However, can you draw something that is 30 dimension? Or can you visualize anything that is higher than 3 dimension? Probably not, right? Probably not. So you say, oh, then that's easy. We just, you know, we just put this coding to 3 dimension. Theoretically speaking, yes, you could do that, but because, you know, it's just kind of like okay, we have a long sequence. I want you to put in a simple rule to remember this sequence, okay? But if I tell you, okay, only use one word to represent the whole sequence, nobody can do that, right? Okay, so see here, this autoencoder is to reconstruct the fashion MIST. But if you only have like 3 dimensions for this coding layer, that's too difficult. That's too difficult of the job to ask this autoencoder to reconstruct, the facial MIST data set. That's just not possible. So when you train this model, it's very difficult for this model to converge. Okay, even when this model converge, okay, it is going to perform poorly in terms of reconstruction. Okay, it's just because you restriction give is too difficult. Nobody can do that, pretty much. Okay, so yeah, I mean, so you can reduce it to 30 dimension, but and you can have a reasonably good result, like what I already show you here. Okay, so this result is, well, it's not satisfied, but you get it's not great, but it's reasonable. It's reasonable. So, okay, so, but now, I mean, if you want to visualize the coding, okay, you want to visualize all the data, I mean, the MIST data set. I mean, but as I said, 30 dimension is just not going to cut it. It's just too, I mean, it doesn't, we human being cannot take anything higher than 3 dimension, right? So what we could do is that there are other algorithms that we know that can do this dimensionality reduction for us. Okay, for example, okay, SNE algorithm. This is one of the algorithms for dimensionality reduction. Okay, TSNE, which actually it's really not a deep learning approach. It's a machine learning algorithm. Okay, so it can I mean, you can use it from scikit-learn. Okay, and then okay, you just give the the x value compressed. Okay, this x value compressed is like from here. Okay, you feed the validation set of your facial MIST as input for your encoder, and you apply prediction on this to get a coding which is 30 dimensions. Okay, and then you call the TSNE model, okay, on this 30 dimension data set to make it 2 dimensions. Okay, and then after you've done that, you can plot it on a 2-dimensional space. Okay, obviously we can now visualize the result. Okay, so you may wonder, like, why do we need to visualize? I mean, all this facial MIST data set in 2 dimensions, because okay, obviously different class is represented by different color. So you can see that. I mean, remember we have 10 different classes, right? Facial MIST, we have 10 different classes, and you will see that the data set with the same class. Okay, each data, for example, all these T-shirts. Okay, the blue points, they tend to cluster together. Okay, the same can be said for the pants. But actually, we have 2 different pants. Okay, but doesn't matter. Okay, for these pants, as long as they are close, okay, they fall in the same cluster. These are the shoes, and you can see that. One thing interesting is that, okay, this is shoes, this is boots, and well, I think they are these 2 are shoes. Are boots. These 2 are boots. I mean, they are represented by light blue. Okay, this is shoes, which are represented by the color, brown color. And the high heel obviously belong to a different class. And you can see all these footwear, all these footwears, okay, are somehow like close to each other. And they fall to different clusters. We know that, but they still, are kind of close to each other, right? Why? Because they look similar. Okay, they look similar. They have certain elements that make them look similar, right? So you can see that, okay, these two-dimensional plots actually allowed us to see the logical relationships between different instances, okay, in the fashion MIST. Okay, how close, how similar two instances are. Okay, you can use this this visualization, result to observe it. Okay. So this is like some, so you can see so far we have demonstrated two applications. Okay, one is dimensionality reduction, PCA to be specific. Another one, well, it's also dimensionality reduction, but we use it for visualization of the data set, right? Okay, but they pretty much both fall into the category of the dimensionality reduction. Okay, so now let's look at another application of the stacked autoencoder. Okay, so if you are tackling a complex supervised task, but you do not have a lot of labeled training data, okay, one solution is to find neural network that performs similar tasks, reuse its lower layer. Okay, transfer learning, we know that, right? So this is something we could do, okay, if you don't have a lot of labeled data. However, if if you cannot find a model that that performs similar tasks, what do we do? If you have a large data set, but most of it is unlabeled, so you already have data set, but and only a limited amount is labeled. So you can first train a stack autoencoder using all the data. Okay, then reuse the lower layer to create neural network for your actual task, and train it using the labeled data. Okay, like something like this. Okay, you can use all the data that you have to train this autoencoder. Okay, and when you train this autoencoder, obviously the input and the output, the label will be just the input, right? Because this is the autoencoder, right? And when you train such an autoencoder, okay, this part, the encoder will compress the information into coding, right? Okay, so this part, okay, after you train this autoencoder, this part, the encoder part, is a good feature detector. Okay, so you can copy the weights to here. Okay, and then you can add like maybe one more layer, as output layer, and use the limited amount of training data set to train this model. Kind of just like transfer learning. Okay, this is kind of just like transfer learning. So this is called unsupervised pre-training, okay, using autoencoder. So we talk about unsupervised pre-training in chapter 11, if I remember correctly. Yeah, but at that time, I couldn't talk a lot about how to do that. It's just because we haven't, really talked about the concept of autoencoder. But once now if you understand the concept of autoencoder, this part will become much more easier to talk about. Okay. And yeah, so I think this part is not much to talk about. Okay. There's a few techniques to train the stack autoencoder. The first one is tying weights. What is tying weights? Okay, think about this. The autoencoder, the encoder, is compressing the input into coding, right? And decoder is decompressing the coding back to the input. To as close as the input as possible, right? So these two parts kind of function exactly opposite, right? Okay, because they work exactly opposite, so not only they look symmetrical, the encoder and the decoder look symmetrical. Remember, I just told you that, right? Not only that, okay, you can actually tie the weights together. Something like this, okay, for example, okay, you can tie this weight to this weight. Okay, the corresponding layers, you can tie their weights together. Okay. Of course, if your weight is like something like here, okay, the weight here needs to be transposed because what you want to do here is the opposite of what you want to do here, right? Okay, so because they are opposite, their tasks are opposite. Will be opposite. So the weight here will be the transpose of the weight here. Okay, so here we go. Okay. Okay. So if you have a total of n layer, okay, and WL represent the connection weight of the L's layer, okay, and then layer n divided by 2, okay, is the coding layer, okay, and the layer n is the output layer, okay. Then the decoder layer weight can be defined, okay, as Wn minus L plus 1 equal to WL transpose. This transpose is important, okay. It's not like exactly the same. It's the transpose of the decoder part, okay, will be the weight of each layer in the decoder is exactly the weight of a layer in the encoder, the corresponding layer in the encoder, weights in the encoder. Okay, so it's a very interesting concept, and to do that, okay, of course you need to be able to tie the weights together. Okay, so you have to define a custom layer. Okay, something like this. Okay, so here the input is a layer. Okay, so you try to, here you try, this is a subclass of a layer, and you try to create a layer, okay, that make use of the layer that you put in, and you copy the weight and shape, but here, I think we here, see, we where is it? Save way. Here, transpose B. Okay, we specify we want to transpose this. The weight of this layer. Okay, and then create it. So how do we make use of this custom layer? It's like this. Okay, so the dense one is like this. dense 2 is like this. Okay, we have 100, we have 30, okay, and then tight encoder, okay, it's like well, we have like a input layer is like a 28 by 28, okay, and we have dense 1, dense 2, okay. This part is not much to talk about. And then in the decoder part, okay, here we use dense transpose. This dense transpose was defined here, right? So this one, okay, we pass the dense 2 that is defined here. So which this will, this will allow us to create a layer which exactly is exactly the same as like a dense 2. Okay, in other words, 30 neurons, zero activation, but okay, with the weight that is like transpose of the dense 2. Okay, and then we use this one to create another layer. Okay, dense transpose to create another layer, and use dense 1. Okay, as the input. Okay, and here we use sigma as output because this is going to be the output layer. Okay, and then okay, we reshape it to 28, 28, and that's it. So you can see we can, we still, put them together, the encoder decoder together to make a tight autoencoder, and then you can train it, just like the previous version. This one is obviously, you can tell it's for facial MNIST, okay, just like what we did, okay, this model achieved a very slightly lower reconstruction error, so which is good, right? So the reconstruction error is slightly lower than the previous version. But think about this, okay? This model with about half of number of parameters, okay, it is able to reach slightly lower error, but with only half of the parameters. Okay, performance is about the same, but the number of parameter is reduced by half. Okay, when you train it, because they are tied, right? So even though, if you think about it, they still have this many parameters, but half of them are tied. So in other words, two, each pair can only be considered as 1, right? Okay, so this model will become much easier to train because the number of parameters is reduced, and the reason, okay, one reason that the reconstruction error is lower. One possible reason is that, okay, because it has a lower number of parameters, which will make it less likely to overfit the training data. Okay. So that's like we can train the stacked autoencoder, in one try. Okay, even if you have multiple layers. Okay, but we can actually train, one additional layer in autoencoder each time. Okay, but how do we do that? Well, I think let's take 10 minutes break. When we come back, we will continue our discussion on this subject. Okay. So, so you may, one of the reasons, okay, stack autoencoder gets its name is because you can train this autoencoder a stack at a time, okay, and this is called greedy layer-wise training. Greedy layer-wise training. So this is especially useful, okay, when you do not have so many methods to fight with vanishing gradient. Remember in the old days, like training deep neural network is so difficult. Okay, so they use this greedy layer-wise training to really achieve like training a deeper neural network. Okay, deeper autoencoder, I should say that. Okay, so it's something like this. Okay, so say this is your original input. Okay, you only train this, so you can see that this is a very shallow autoencoder, right? So training this doesn't require a lot of training data, and it is more likely that you can you don't need to go through a lot of trouble, okay, to be able to train this model, because it's a shallow model, right? It's not so deep, right? Okay, so you don't need, for example, like you don't need a dropout, you don't need like a batch normalization, you don't need like a initialization strategy, or even like if your activation function is not ideal, okay, maybe you can still get this shallow autoencoder trend, right? Okay, and then okay, when you get try to I mean, this is original input, right? And I mean, try to preserve all the coding result of all your input. Why? Because we are going to use that to train another set of autoencoder like this. In this one, okay, the input is going to be the coding output of the original input. Okay, so this size is going to be exactly just like this. Okay, so this hidden one, in some sense, is going to be the input layer here, and you have another smaller, well, depending on your application. Okay, you have another a layer like this. Okay, and you have output layer, which again it's a shallow autoencoder, right? And this output layer size will be the same as this input, right? And you can train using not much training data, and again, because it's shallow, so you don't need to worry about like a vanishing gradient that much, I mean, So once you finish training, okay, you can copy the input. I mean, you can make a stack up these two autoencoder together to make a deeper autoencoder. So you copy the hidden layer from here, the weight of hidden layer from here. You copy this one to here. You copy this one to here, and you copy this one to here. Okay, so this is the way to train one autoencoder at a time, and you can stack up these separate different autoencoders together to form a deeper, more complicated autoencoder. Okay, this technique, okay, is called greedy layer-wise training. Okay, so you may ask, well, but when we are talking about this one, we just train this directly, right? We don't need to use this greedy layer-wise training. So why do we need to talk about this? Is this required? Let me put it this way. No. Okay, this is no longer required. Why? Because remember in chapter 11, we learned all those techniques to train a deep neural network, right? So we can train this model from scratch directly. Okay, this is no longer considered an impossible task, okay, nowadays. However, back to old days, like 1990, even like early 2000s, okay, to train a deep model is still a difficult task, okay? So they use this greedy layer-wise training, okay, to gradually stack up a deep neural network, okay, a deep autoencoder, okay. You may wonder, like, yeah, I mean, so why do we need to eventually create a deep autoencoder? The reason is that, remember, just like the application we just talked about, eventually we could use this part for transfer learning, right? We can use this part for transfer learning. Okay, and because training autoencoder does not require label the data set, right? Okay, and we only need just a limited amount of label data set, okay, to do transfer learning from the encoder, okay, of the deep autoencoder, okay. But so, okay, I think I already explained, okay. So this one way to trigger the current tsunami of the interest in deep learning is a discovery of the 2006 by Jeffrey Hinton. So they use unsupervised pre-training, okay, to using the greedy-wise layer approach, okay. Of course, they use the restricted Boltzmann machine, okay. So for the unsupervised pre-training, but Joshua Bengio in 2007, they showed that autoencoders work just as well. Okay, just you don't need a restricted Boltzmann machine for to train a deep like autoencoder and then use that for transfer learning. No, you can use autoencoder. Okay, so but nowadays it's not necessary because we learn so many good techniques from chapter 11. So we can just train a deep neural network, in one shot. Okay. But understanding this greedy layer-wise training is still a good idea because why? Because you can still see this technique being used in some, papers here and there. Okay. Of course, the paper may be like more than 10 years old, but when you do like a literature survey, I mean, sometimes you will encounter this type of stuff. So you need to understand what that listing is. Okay. So far, the autoencoders that we have discussed are based on dense layers, right? Pretty much MLP, right? But obviously, you can use the same concept on convolutional neural network. Okay, you can use convolutional layer to create autoencoder, and you can even use the recurrent layer to create autoencoder. Okay, so let me show you. Okay, one of the convolutional autoencoder. Obviously, if your input is pictures, the convolutional layer process pictures much better than the dense layer, right? So yeah, so this is an example. Okay, you see here. Okay, we directly treat it as like one channel. Okay, 28 by 28 like input. So we use a convolutional layer, conv2D. Okay, with 16 feature maps. Okay, and kernel size 3, padding same, elevation 0, and then we try to reduce the dimension by using max pooling. Okay, with pool size 2. Okay, and then we use another convolutional conv2D with 32 feature maps, and same. Kernel size 3 and same padding and 0 excavation, and then again we reduce dimension by height and width by 2. Okay, and then we have 64 feature maps and the same arguments, and then we reduce the dimension further, okay, by 2, okay, on both width and height, and this is our encoder. Okay, but you may say like, well, how do we do the decoder part? Because the decoder, okay, when we in the CNN we normally shrink the input, but but here, okay, we need to, in the decoder we need to enlarge it back, right? We need to enlarge it back to the original size. So what do we do? Okay, remember we have transpose convolutional layer. Okay, the transpose convolution, we talk about transpose convolutional layer in like super resolution, right? We talk about that, right? We can enlarge the input by using the conv 2D transpose. So you can see here we use a conv 2D transpose. Okay, we now convert it to 32 feature maps, and kernel size 3, stride 2. Okay, this stride is actually 1/2, right? You know that, right? This basically means we stretch the feature map by 2 by size. I mean, we stretch the width and height by, we double the width and height. Size, and parity is valid. Evaluation 0, input shape is 64. Okay, 64 because we get it from here. Okay, and then okay, because we have like this stride 2, so we enlarge it. Okay, and then we use the similar setting to enlarge it again, and then we cut the feature map by half as well. Okay, and then we cut it into one, and then stride 2. I mean, we enlarge it once more, and now we for each pixel we still use sigmoid. Okay, we still use sigmoid. Okay, this part is the same. We still treat each pixel as like a binary classification. Okay, and then we can combine this conv encoder and the conv decoder to form a conv autoencoder, convolutional autoencoder. Okay, so this one you can also train it, and and it works well for the facial MNIST. You can obviously change this one to work with any image input. Okay. Okay, so you can also create a recurrent autoencoder. Okay, so this is an example. Okay, so this one, okay, we actually treat each image. I mean, in the facial MNIST, okay, we treat it like a layer, row by row. So we have 28, okay, rows. Okay, each row has 28 pixels. Okay, so you can see that. Okay, here we use the LSTM. Okay, with 100 neuron. Okay, and the output is sequential as well. Okay, and the input shape is non-28. That means like each input, like we treat like is each row is 28. We just get, any number of rows, okay, from the input. And then, okay, this is our coding, okay. So we get like 30 neurons. This is for the coding. This part is our recurrent encoder. For recurrent decoder, okay, this Keras dot layers dot repeat vector 28. Input shape 30. That just means like we try to, at each time step, we just have this coding output these 30 values in order to create a sequence, okay, for the following recurrent layer, okay. So then we have a 100 neuron, okay, and return sequence to be true, okay, and then the last one, okay, again we use time distributed chaos layer dense 28 elevation sigmoid, okay, and that's it. So you can combine these two to form a recurrent autoencoder. So now you see that we can create autoencoder using dense layer. We can use autoencoder. We can create autoencoder by convolutional layer. We can also create autoencoder by recurrent layer. Okay, so all this can be done. Okay. So I think I already explained this one. Okay. So far all the autoencoder that we have talked about, okay, are what we call under-complete autoencoder. There are other type of autoencoder called over-complete autoencoder. Okay, the under-complete autoencoder, as I said, most of the time is used for the dimensionality reduction. Okay, and remember we try to make autoencoder difficult in reconstruction in reconstructing the input, right? In the under-complete autoencoder, the coding layer dimension is already its difficulty in reconstructing the input, right? Because well, the dimension is lower than the input, so you have to find a good way to represent the input, right? But in over-complete autoencoder, that means well the coding is not necessary. It's equal or greater than the input dimension. So obviously, in such a scenario, the difficulty part is not, okay, the difficulty of reconstructing the input doesn't come from the dimension of the coding, right? So we have to inject some other difficulties in order for this autoencoder to learn something. Okay, so there are actually many kinds of constraints that can be used. Okay, including one that allow the coding layer to be just as large as the input, or even larger, resulting in over-complete autoencoder. Okay, so for example, denoising autoencoder. Okay, this denoising autoencoder, okay, is like this. Okay. We force autoencoder to learn useful feature to add, okay, so we intentionally add noise to its input, okay, and we train it to recover the original noise-freed input, okay. So in the training, we add the noise by ourselves. So we still know what the original input is, okay? But we intentionally add the noise, okay? There are two type of noises we normally add. The first one is Gaussian noise, or what you can call like a white noise, okay? Which makes like you can inject this input, in the input, okay? The other one is like randomly dropped, randomly switch off input. This is also considered as one of the noise. Okay, basically it just means like at some point of time, like some input gets dropped. Okay, this can be mimicked by using the dropout. You can apply dropout on the input layer. Okay, so in terms of figure, it looks like this. Okay, if it's Gaussian noise, you just inject it here. This is your input. Okay, and you go through this autoencoder, and you try to train this autoencoder so that it can reconstruct the input. Okay, and this input will be as close to this one without the Gaussian noise. Okay, you train it. When you train it, you try to do this, and after you finish training, after you finish training, you no longer add the Gaussian noise. Okay, you no longer add the Gaussian noise. The input will already contain the noise, and your autoencoder will be able to remove those white noise from the background for you, and to output like the noise-free result. Okay, and for the rendering switch of like noise, I mean, you just try to add a dropout layer on the input. Okay, to randomly switch off certain input. Okay, during training again. After training, we know dropout, I mean, doesn't work after, I mean, when we do the inference, right? So this layer is like automatically disappear. Okay, I mean after training. So I mean we can use this autoencoder to sort of like reconstruct or like fill in the missing values. Okay, or you can call it imputation. Remember in the previous slides, I told you there are two things. Okay, I mean the forecast and the imputation. Okay, I mean in the RNN part. Okay, and so this is perhaps the first model in this class I talked about. Like we can impute the data. Okay, so here is like one of the example. Okay, of the denoising autoencoder, and here we use randomly switch of input noise. So this one work with like the fashion MNIST. So you can see that here. Okay, we have the flattened input. Okay, and we apply the dropout. Okay, the dropout rate is 0.5. So half of the inputs will be turned off. Okay, at random, right? Because the dropout rate is 0.5. Okay. So, and then we have like a dense layer of 100 neuron, zero activation, 30 neuron, okay, and zero activation again. So this is a coding layer. And so that's the encoder. For the decoder, we have 100 neurons, okay, for the first layer with zero activation. And we also get input from the coding layer, so it's 30. Input shape is 30. And then we convert it back to 28 by 28 with sigmoid activation, and then we have to reshape it back to two-dimensional. Okay, and then okay, you can combine this dropout encoder and the dropout decoder together to be a dropout autoencoder. So this one, okay, because of this dropout layer, during training, half of the input, okay, will be turned off at random. Okay, so but this autoencoder is going to learn to reconstruct the missing values, and yeah, this is well, even though I say like denoising autoencoder doesn't need to be under complete, but this example happened to be also still under complete autoencoder because the coding layer dimension is much lower than the 28 by 28, right? But I mean, this doesn't have to be 30, okay? If you want this to work even better, you can change this value to become like maybe like a 700 something, okay? Just like the input size. But anyway, okay, so if you try to draw the result, okay, you can see this is actually the input after dropping out 50% of the input. So if you don't see the lower row, can you tell what they are by looking at this input? The only thing you can probably tell is maybe, oh, this one looks like a t-shirt. This one looks like a long sleeve. This one looks like a shoes, right? Okay, like it looks like high heel. Okay, But well, for these two, it's probably difficult to tell. Okay, but the reconstruction is very reasonable, right? The reconstruction is very reasonable. Okay, so this tell you, okay, you can use autoencoder to fill out the missing values. Okay, even when the missing value, okay, you have 50% of the missing value. I mean, you can still, the autoencoder can still, find a way to do a good job for you. Okay. So now, okay, we talk about like already finished another application of autoencoder, which is like get rid of noise, either the white noise or like doing the imputation for us. Okay, and the next one is called a sparse autoencoder. What is sparse autoencoder? Okay, sparse autoencoder is trying to do feature extraction. Okay, we try to make the coding layer, okay, to activate as little as possible, and by enforcing the coding layer to react as little as possible, okay, or enforces what we call sparsity, okay, then the coding layer is going to kind of represent like important features. Okay, each dimension is going to represent like one important feature. Yes.
So in the coding layer, not every neuron is active. That's normal.
Yeah, of course. But now we want it to react even lower than that. Okay, I will tell you. I mean, what we are doing here. Okay, give me. Let's finish this one. If you have more questions, you can ask. Okay, so for example, it may be we may push like the coding layer to to have average only 5% active neurons in the coding layer. Only 5%. That's much lower, right? Much lower. Normally, like the coding layer. I'm not saying coding layer has to be like active all the time, or I mean all of them have to be active all the time. But at least like the coding layer, like normally we don't put the restriction for the coding layer to activate. Okay, but now like we intentionally make the coding layer to only react or to activate only 5%. Okay, something like that, in order to enforce this sparsity. Okay, so you may ask, so why does this become a good feature extraction? Okay, I mean it's just like if I give an example. Okay, if I put a restriction on you, say like you can only speak like a few words per month. Okay, then I mean you would probably just say some very meaningful words, right? Every time you open your mouth, the words you spit out must be very meaningful, because I put this restriction on you, right? So this is like exactly just like this. Okay, I mean for the autoencoder as well. Okay. So how do we put the restriction on the coding layer? Okay, one way to do it is, remember you guys have learned the L1, right? Okay, so you can see for this one, okay, we call it sparse L1 encoder. So I mean the other part is the same, okay, as like the previous one. The only difference is that here, okay. But by the way, this is the over-complete autoencoder. So you can see this, the coding layer, the dense layers, is 300 neurons. It's it's still not as big as the input, but it's a lot bigger, right? So 300 activation sigmoid, and see we put additional layer called activity regularization. L1 equal to 10 to the power of negative 3. So this is a very small value. This is a very small value. And the other part remains the same. Okay, and we combine this sparse L1 encoder and the sparse L1 decoder to form our sparse L1 autoencoder. So when you train this neural network, this autoencoder, okay, your coding layer will not react like so frequently because we actually try to make sure like the activation, okay, or its output, okay, the L1 value of this layer, okay, is going to be lower than 10 to the power of negative 3, okay. So so this is like one way to enforce this sparsity, okay, and so using the L1 norm rather than the L2 norm, okay, will push neural network to preserve the most important codings. Because we know L1, okay, when you use L1, it will only leave like a few neural network to be non-zero, okay, and the other, they'll push the other to be 0. But if you use L2, they'll push all the neural network, all the neurons to output small values, but they will, it will not, eliminate the output of like the other neurons. Okay, so normally we use L1. Okay, but so this is like just one way. Okay, but this normally doesn't perform very well. Why is that? Okay. What should I say? Okay, it's like this. Okay, when we want the sparsity, okay, it's like we want, say like okay, if this class is an autoencoder, say this line is the coding. Okay, it's a coding layer. So we have three neurons. So when I put these restrictions, okay, by using this L1 regularization, I only restrict like the sum of these 3 neurons, right? But sometimes I want to enforce. What I want to enforce is like, okay, say like I want like the neurons, each neuron in the coding layer to only activate like maybe 10% of the time. Be very careful. Here I want each neuron, so you react 10% of the time, you react 10% of the time, and then the third one react only 10% of the time. So it's not like the sum of you guys. I want to enforce like each neuron in the coding layer separately. Okay. So this is also sparsity constraint, but you can say the resolution of such constraint is even much stronger, right? It put a much more stronger constraint on every neuron, okay, instead of just a group of neurons. Okay, so how can we achieve that? Okay, to measure the actual sparsity of the coding layer at each training iteration for each neuron, and parallelize the model when the measured sparsity differs from the target sparsity. Okay, we do so by computing the average activation of each neuron in the coding layer over the whole training batch. So first, obviously, if you want to do that, the batch size has to be big enough. If the batch size is too small, then I say, 10% of it, because this 10% is computed based on one batch, right? So that 10%, if each batch you only have like a very few instances, then it's probably not going to, the calculation of 10% is not going to be very accurate, right? So the batch has to be, at least not too small. Otherwise, the the mean will not be accurate. Okay, so once we have the mean activation per neuron, okay, so this is enforced per neuron. Okay, so we want to penalize the neurons. Okay, but okay, that are either too active or not active enough. Okay, in L1, we only penalize, if the group of neurons active too much, right? But if the group of neurons doesn't active that much, we doesn't penalize it, right? So this one is much, put a lot like granularity of, in terms of restriction on the coding, the neuron in the coding layers. Okay, so for example, if we measure a neuron has average activation of 0.3, like 30%, but the target sparsity is 10%, then it must be penalized. Okay, but if this neuron, the activation is 0.05, only 5%, and the target sparsity is 10%, that neuron will also be penalized. Okay, it's not just like when this neuron activates too much. When this neuron doesn't activate at all, we also penalize that. Okay, so we have this target sparsity that we want every neuron to achieve at least as close as possible. Okay, this is very different from the previous approach. Okay, so one way is to add the square error. Okay, like to the cost function, right? But in practice, okay, we normally use like what we call KL divergence. Okay, the fullness callback library. This is like my pronunciation may not be accurate because this is these two guys. This is the name of two guys, but they are Germany. Okay, so I'm not sure if my pronunciation is correct, but the abbreviation is called KL divergence. This KL divergence, okay, is a famous mathematical tools to measure the how far away two distributions are from each other. Okay, so it quantifies how far two distributions are from each other. Okay, if two distributions are exactly the same, the KL divergence result is 0. Okay, you get the idea. Okay, so basically, okay, I will not go into the detail. Okay, how to derive this KL divergence, but chapter 4 talk about this, but we didn't talk about chapter 4 anyway. Okay, but it has much stronger gradients than the mean squared error. So that is why, okay, when we use this for training, okay, we get more gradient. Okay, that help us to train this model much faster. Okay, so here just to show you, what the KL divergence value looks like. So you can see, okay, so if it's MAE is like a mean absolute error, so it's like just like linear, right? The error is just linear, but MSE is a square root error. So sorry, it's this red line, but the KL divergence is represented by the blue line, and you can obviously see that this blue line has a much stronger gradient than the other error function, right? So that's why, okay, you can, we prefer to use KL divergence here, and this is how we construct, compute the KL divergence. Okay, because we are talking about discrete probability distribution. Okay, so the calculation is like this, and here, in our application, because it's even easier. Okay, it's not exactly a distribution. It's just like the probability of the activation, right? Okay, it's just one value, right? Just one value. Okay, maybe the target sparsity is 0.1. That means 10%, right? Okay, 10%. That's our distribution, right? Okay, just represented by a value p, and so if our target probability is p, and the current activation is q, then the KO divergence computation can be converted to something like this. Okay. So then, okay, there's another hyperparameter called sparsity weight. Okay, because think about this. Now you have a cost function. The cost function is constructed by two parts. The first part is like a reconstruction loss, right? Reconstruction loss basically penalize the model when the autoencoder doesn't reconstruct the input well, right? That's a reconstruction loss. The other one is this, sparsity loss, right? Sparsity loss. You can imagine, okay, when you set this sparsity to only 10%, okay, this is obviously a constraint for the coding layer, right? Okay, and when you put the constraint for the coding layer, it makes the reconstruction more difficult, right? It makes the reconstruction more difficult. So these two cost terms are somehow like what should I say, like have different purposes, and these two different purposes are kind of fighting against each other, right? Because, well, if you want the reconstruction to be as successful as possible, you shouldn't put any restriction on you shouldn't put any constraint on the coding layer activation, right? Okay, but on the other hand, if you put a coding layer constraint, activation constraint, then the reconstruction will be constrained, so it will not perform very well, right? So for these two terms, okay, so we have this sparsity weight. This sparsity weight is multiplied to the sparsity loss, okay, and if this value is bigger, it means you care about this sparsity constraint more, and you do not care reconstruction loss that much. If this sparsity weight is small, that means you care about this reconstruction more, and you doesn't care that constraint that much. Okay, just want you to be to have an idea what this sparsity weight. But in general, this sparsity weight is like value is in between 0 and 1, and you don't need to set a large value for this. I mean, maybe set a 0.1 or even lower than 0.1. Normally can get you to a very good result already. Okay, so here we want to implement this sparse autoencoder. Okay, so first we create a custom regularizer to apply the KO divergence regularization. So this one is like the KO divergence is just like this is just we can call this callback library divergence. Okay, from we just get the loss from here. Okay, and then here it's just like we just define this. This is like we compute the KO divergence by using the target, okay, and the mean activation, so this part is actually just like exactly this one, okay. So you finish this one, and then you multiply this to the weight. This weight is the sparsity weight hyperparameter that you get from I think we get it from the parameter, input parameter. Okay. So anyway, so once you have this this loss, okay, like a KO divergence loss, ready, Okay, KO divergence regularizer ready. Then, okay, here, okay, we first create an object of this, and we specify the KO divergence. The sparsity loss is weight is 0.05. Target, this is a target activation is 10%, 0.1. Okay, and then here, okay, you see, again, this is fashion MIST, so you have like input shape 28 by 28, and then 100 neuron zero, so 300 and sigmoid activation. So we, set activity regularizer to be this KLD reg, okay, that we already created there, okay, and then in the decoder remains the same. And then we combine this encoder and decoder to form our sparse KLAE. And if you train this model, okay, and you, when you see how it reacts to your data set, you will find that, okay, for example, here, okay, actually 90%, okay, of the percentage of activation, okay, for the neuron have the percentage of activation like within like 0.1 to, lower than 0.2. Okay, average, I think the average is like 1.1, okay, 1.1. And this one just means like neuron mean activation. And you can see, most of them, their average is like 0.1. Okay, so this is to just show you, okay, the sparsity autoencoder is doing a very good job. So each neuron will actually represent different meaning, okay, in the coding layer, basically. Okay, when that one is activated, you can imagine, okay, the input must mean certain something, okay, so you can sort of like explain that using the features represented by the neurons in the coding layer. Okay, so sorry to take you a little bit more time. So let's take a 10 minutes break. When we come back, okay, we are going to talk about the last subject of the autoencoder. Okay, so so here we are in a position to talk about the last application of the autoencoder, okay, which require another type of autoencoder called the variational autoencoder, okay. So this was proposed in 2013 by Dedrick Kidma and Max Whaling, okay, and this one has become one of the most popular type of autoencoder. Okay, why? Okay, because this is very different from all the autoencoders that we have talked about. Okay, this one, okay, there are two important differences. Okay, the first one is they are probabilistic autoencoders. Okay, what do we mean by probabilistic autoencoder? It means that the output are partly determined by chance. So the same input may result in different outputs. Okay, the same input may result in different output. But we know, like in the previous autoencoder model, okay, yeah, the same input always give you the same output. Okay, of course, like you may argue, okay, how about denoising autoencoder? Denoising autoencoder, we intentionally inject some noises in random, right? Either Gaussian noise or like randomly switch off noise. But if you don't consider the randomness in those noise, then the same input will still give you the same output, right? Okay, so this is like for the past all type of all the types of autoencoder that we have talked about. Okay, none of them will be considered as like a probabilistic autoencoder. Okay, but variational autoencoder is a probabilistic autoencoder. Okay, and the second most important reason, this actually is the most important reason why variational autoencoder become so popular is because these variational autoencoders are generative autoencoders. It means that they can be used to generate new instances that look like they were sampled from the training set. So, yeah, in a sense that you can use it to generate a lot of data. Okay, so this is these two properties make the variational autoencoder very similar to RBM, restrict Boltzmann machine, but it's much easier to train. And because we didn't talk about variational restrict Boltzmann machine, so you probably don't need to worry about that. Okay, but you need to understand variational autoencoder. Okay, perform variational Bayesian inference. Okay, which is efficient way to perform approximate Bayesian inference. Which is was discussed in chapter 9. Okay, if you want to know more about variational autoencoder, you can check out chapter 9 material for detail. But again, I don't have time to go back there to talk about this. Okay, let me show you how variational autoencoders work. Okay, so this is a variational autoencoder. Okay, the input goes through several hidden layers. So this is the encoder. Okay, and it will be used to generate mu and sigma. Okay, this mu is an average of this sample of this particular instance, this input instance, and the sigma is the standard deviation for this particular input. Okay, and this mu and the sigma will be used. Okay, so assume this is like a input space. Okay, and then somehow this input space will be converted into a coding space like this. So even the input space may look very different, may look very with a special shape or very biased. Okay, eventually they will be converted into a Gaussian distribution. Okay, Gaussian distribution. Okay, and then remember, so this one will generate a mu and a sigma, right? So mu will be used to determine where that location is in this Gaussian distribution. Okay, and sigma determine the range. And then you are going to use this mu and the sigma to randomly sample a point from this distribution. Okay, this randomly sampled point, will be very close to this input instance, but not the same. Okay, because they have the same mu and the same sigma. Okay, you just use this mu and sigma to do the sampling to get you another instance here. Okay, and this one will be converted back to the original shape. Okay, original we are going to reconstruct the input. Okay, using this instance. Okay, trying our best to reconstruct it by using this decoder. Okay, so that's the concept of this variational autoencoder. Okay, so this Gaussian noise, mu plus the Gaussian noise times the sigma. Okay, this is like a use for sampling. Okay, this part is used for sampling and to get an instance. This instance, as I say, is close to the mu and the sig. That particular instance you get from the input, but not the same, not necessarily the same. Okay, so okay, I think like I already explained what this is. Okay, so we can look at the cost function. Okay, it's composed of two parts. The first is the reconstruction loss. I mean we use all the time. Okay, which pushes the autoencoder to reconstruct the input as close as possible. Okay, and the second part of the cost function is the latent loss, which pushes the autoencoder to have codings that look as though they were sampled from a simple Gaussian distribution. So the second loss function will push this input space into this coding space that is what should I say, like as close as like a Gaussian distribution. Okay, so and we call that coding space, okay, as the latent space. Okay, so end up it's going to look like a cloud of Gaussian points. Okay, so after training a variation autoencoder, okay, you can very easily generate new instances by just sampling a random coding from the Gaussian distribution and decode it, and that's it. Okay, so basically like it's a very easy to use. So far all the applications of the autoencoder that we have seen, okay, all the applications that we have seen for the autoencoder are using encoders, right? Right. Think about that. Okay. Well, the only part that is different from, for example, like dimensionality reduction using encoder, right? And transfer learning, the pre-trained. We remember like the greedy layer-wise pre-training, and eventually we use the encoder part for transfer learning, right? Okay, but the only difference is that, okay, for the denoising autoencoder, we use the whole autoencoder, right? But this is this variation autoencoder, or I probably should say like because when we use it for generative model, the decoder is the part we use the most often. Okay, so this is like a very different from the other ones. Okay, so so variation autoencoder is latent loss. Okay, this is probably a little bit difficult to explain. Okay, L just means latent loss. Okay, K is like the size of the dimension. Okay, or you can say like a number of instances. Okay, and the sigma I and the mu I are the standard deviation and average of each instances. Okay, I mean, so this is like this construct a variational autoencoder, latent loss. Okay, I will not get into the detail, mathematical detail here, but if you are interested, in knowing more about this, you can check out chapter 9 and also perhaps some additional material, okay, for the mathematics behind that, okay. So, so here, okay, so you can, you can have like you can first create like this sampling, basically like a given a particular like mu and standard deviation sigma, okay. We try to get like a new sample, okay, by using this sampling, okay, function, okay, and oh, by the way, probably I should say here there's like I forgot to mention about this, okay. We use a gamma equal to log sigma square, okay, to replace the sigma, because this will help us to when we train the model, this will actually help us to converge faster. So once you replace log sigma squared by gamma, okay, the original function like this one will become like gamma I, right? And this part will be converted into exponential of gamma I. Okay, so the other part remains the same. So that's an interesting twist. I mean, we call that a trick that we can use for the variational encoding. And here, okay, in this sampling function, we actually make use of that the gamma trick. Okay, gamma tweak. Okay, so you can see we have a log var that represent that gamma actually. Okay, so and then we create an encoder. Okay, here we are using a functional API. Okay, because model is not entirely sequential. Why? Because you can see here for this one we are outputting we have two outputs, right? We have two outputs. So this one cannot be, created by the sequential API. So you can see that, okay. So first, we assume our coding size is 10, okay. As for like what size of the coding you want to use, okay. Again, this is dependent to like what should I say? Like the complexity of the data that you want to generate. Okay, here because we are dealing with like fashion MNIST, so fashion MNIST 10 dimensions should be good enough. Okay, so input is kernel is a chaos layer. Okay, input is 28 by 28. I mean this is nothing to be surprised with, right? So and then okay, so we use this input, okay, and flatten it. Okay, so this is the flattened input, and then we use 150 neurons. Okay, activation residue. We get the previous layer as the input, and then we use this one as a Z, and then feed it to like 100 neuron zero activation. So we have another layer. Okay, and then after this, okay, so you see. For the same layer, okay, the same layer will be used to create the coding mean. Okay, so this Z, okay, we use a dense layer to create this coding mean, okay, and we also use the same input to create the coding log var, which is gamma. Okay, using the dense layer. Okay, so you can see this part is the part that we cannot use the sequential API. Okay, because obviously we have more than one output. Okay, so coding equal to sampling. Okay, so you put this coding mean and the coding log var together, and then you call the sampling. Okay, remember we have this sampling function, sampling defined here. This is also this is also a layer. Okay, but this layer, the purpose of this layer is this one, to come up with a sample for the decoder. Okay, and then once we have that, okay, we create a variational encoder. Okay, so here we have one input, but we have output. We have three items: coding mean, coding log var, and the codings. Actually, the only one that is useful for the decoder is this codings. These two, okay, are the byproduct or like are necessary to create the codings. But other than after we create the codings, okay, the previous two items are no longer useful. Okay, so this whole thing is the encoder. Okay, and then okay, we can also create decoder. But now, okay, decoder is much easier. Okay, we could use sequential API if we want. Okay, if we want, because you can see here, okay, the decoder is this part, But this part is, it doesn't have a very complicated, structure. So we could use the sequential API, but here we still use the functional API, okay, just to be consistent with the previous one. So here we just get the input from the coding size, okay, which is like 10, and so we get it, and then okay, we use this one as the input for this dense layer, 100 neuron, 0 activation, okay, and then the output will be used for the input of the next layer with 100 neuron, 0 activation, and this output will be used, okay, for this 784, okay, neurons, activation sigmoid. We still treat each neuron, each output as like a binary binary classification, okay. So we still use sigmoid, okay, and then we reshape this to 28 by 28, 2 dimension, okay, and then okay, the variational decoder, okay, we put them together. So decoder input, output is output, okay, that's it. And when we put them together, okay, the variational encoder, okay, input, okay, get input. The output, the first 2 parts are not used, even though we know like the first one is the mean, the second one is variance, but we are not going to use them anyway. The only one that is useful is the coding, okay. So the first 2 are just a placeholder, okay, and then we'll use codings for the input of the variational decoder. Okay, we call it reconstruction. And then, okay, we use these 2 to create a variational autoencoder. Okay, and the input, input is input, output is reconstruction. That's it. Okay. So we ignore the first 2 output. I think I already explained, and so finally, we need to add the latent loss and the reconstruction loss. So this is like where we create that latent loss, and so the variational so we add this loss, latent loss, okay, to the loss function. But the one thing you probably want to notice is that, okay, for the reconstruction loss, because this reconstruction loss is like a binary closed entropy, right? And the binary closed entropy is computed for each neuron. Okay, but this latent loss, when we calculate it, this is actually for the whole picture. Okay, so because they mean different things, right? One is for one neuron, the other one is for the whole picture. The whole picture has 28 by 28, this many neurons, right? So in order for them to be the same, to have the same, to represent this for just one neuron, okay, on average. So we have to divide the latent loss by 784. Okay, the reason to divide this one is so that, okay, this latent loss is average, so that we put this latent loss on each neuron. Okay, so we add this one to the loss, and then loss is binary closed entropy, and we use RMS prop. This is also special. Okay, the previous ones you can see that we use like SGD. But this one we use RMS prop. Why is that? It just happened that RMS prop works better for this variational autoencoder. You can try different optimizer and see like which one is better. Okay, by yourself. Okay, and then I think I don't need to explain this. I already explained. Okay, so then you can train this variational autoencoder. Okay, again, using this training set and using the same training set as the label, and you train it for 50 epochs. Okay, batch size 128. Okay, validation. I mean, again, using the same validation as like the label for the validation. Okay, and then once you are done, okay, so you can use this variational autoencoder to generate images that look like fashion items. So all you need to do is to sample random codings from Gaussian distribution and decode them. So here, okay, for example, codings, okay, you just use tf.random normal, okay, shape, okay, you want to generate 12 like instances, okay, of the coding result, okay, and the code. I mean, so because coding size is 10, right? So you generate 12 of these coding size, instances, okay, and put it in the codings, and then you use the variational decoder. Here, see, as I said, we use the decoder for as a generative model. Okay, so this is important. After we train this variational autoencoder, the decoder is the one that we actually use. So we call it. We put the codings there, and then the result, okay, will be put into images. And then if you draw these images, okay, the figure is going to look like this. Not exactly. For example, you can see some pictures are still blurred, right? The pictures are still blurred. This one doesn't. This looks like a purse. It looks like a purse, but it's not very clear, right? But at least you can see that this represents like a fashion items without any problem, right? You can observe that these are fashion items. Okay, so this is like but these fashion items are generated from random numbers. Okay, we are not reconstructing this from the data set. We are using these randomly generated numbers to generate these pictures. Okay, and the one thing even more interesting, okay, is that we can do what we call semantic interpolation. What is semantic interpolation? Okay, we still have time. Yeah. The semantic segmentation is, okay, instead of interpolating two images at the pixel level, okay, I mean, normally when you do interpolation, okay, for example, you say, oh, we just add up these two images, pixel by pixel, and then divide by 2, right? What you are going to get is like, well, you can probably see like something from, some image from here and some image from here stacking up together, right? But that doesn't look good, right? That doesn't look good, okay? So that's like a regular interpolation that we can do. We normally do for images, okay? But what semantic segmentation is like this, okay? Remember, all these 12 items are based on 12 randomly generated coding vectors, right? Right? You know that, right? So you can imagine each of them represent a coding vector. Okay. Now, okay, what we can do is like this. We can this is a vector, this is a vector. We can add up these two vectors and divide it by 2. So we will still have a vector, but this vector is going to be somewhere in between these two, right? Two vectors, right? It's going to at the middle of these two vectors, and then we use that vector to generate an instance by using this generative model. Okay. So actually, what we can do is here. Okay, we actually try to remember this is 3 by 4, right? 3 by 4. We enlarge it. We enlarge it to 5 by 7. we intentionally insert some spaces between the column and the row. So of course, when you insert the space between the column and row, you have some empty space to fill, right? So for those empty space, okay, this TF reshape is going to automatically create the interpolated vector for you. Okay, and then you feed these interpolated codings into the variational decoder, this generative model, and what you are going to get is this one. So you can see this the one with like bounding boxes are the ones that originally in here. This is 3 by 4, and then here we have this 3 by 4. And in between, okay, those are the, we generate the, interpolation. I mean, we use an interpolation of these two vectors to generate this one. And then you have a vector, and then use a generating model to generate this one. So you can see, for example, these two are shoes, right? So the interpolated one is shoes. Right? That's meaningful, right? Okay. So for example, what else? Anything else? For example, like clothes. These two. Well, this is t-shirt. This is dress, right? So this one, it looks like a short sleeve dress, right? So again, this is like interpolation of these two. I mean, but this is semantic interpolation. This is not like a real pixel by pixel interpolation. Okay? So this is a very interesting thing to create. For example, or like anything else. Let me see. Yeah, these two are shoes. So this is a purse actually, but this one is also shoes. Anything else? Yeah, so the other part, I think, I mean, for example, these two are clothes. I mean, this is dress, this is clothes, and we still get a clothes here. Okay, so you can somehow see like if two items are similar in certain property, and you get like a semantic interpolation between these two items, that item will still be like that. Will still share the same property. Okay, so I think some of them are, if they are very different. I mean, of course, for example, like these shoes and clothes, then the semantic interpolation between these two will not be able to guarantee what this is. In this case, it's probably shoes, but it's not very clear. Or for example, like shoes and the dress. In between, this is pants. So this is very, it doesn't guarantee any special property. But if it's like in between shoes, then this one must be shoes. If it's in between dresses, clothes, then the middle one must be clothes. Okay, that's the semantic segmentation, interpolation. Okay? Just want you to be aware, okay, that this variational autoencoder, especially the decoder part, can be used as a generative model. I mean, but obviously it does not, the image that this variational autoencoder generates doesn't look so good, right? Okay, of course, part of the reason is because, okay, yeah, I mean, the model that we have here, okay, it's a relatively simple model. If you want to increase the complexity of the model, yeah, it may perform slightly better, okay, but yeah, the autoencoder still has its limitations, okay. When you use it to generate the the data set, it's just not that good in terms of quality. Okay, so if you want to really generate some data in good quality, yeah, you have to use GAN, Generative Adversarial Network. Okay, but yeah, I mean, yeah, due to the time limit, we are not able to talk about that. And that's actually like the next topic. But yeah, we only have like 5 minutes left. Okay, less than 5 minutes. So yeah, so that's about it for this semester for the generative adversarial networks. I mean, if you guys are interested, you are more than welcome to check it out yourself. I mean, you can see, I mean, we can actually use it to create like a much realistic result. Okay, for example, not only we can do like, for example, we can use, we can do vector arithmetics for vision. So for example, for example, I mean, these are the codings. If you use their codings, and then, okay, you do an average, then you get, because these three are male, right, with glasses. So you get a male with glasses, okay? And these three are male without glasses, and you do an average for their codings, and you get a male without glasses, okay? And then these three are female without glasses, right? So you do an average of their coding and generate an image. This will be a female without glasses. You can even do arithmetics, okay? Male with glasses minus male without glasses plus female. It becomes female with glasses. Very interesting, right? This is called vector arithmetics. But you cannot probably expect that for variational autoencoder because, I mean, the quality is not that great. Okay, but this one is for like a DC GAN, okay, paper. Okay, so it's very interesting result. Okay, but this is only good for the GAN model. Okay, so I guess that's about it for this class. Any question?
可是 GAN 在设计的时候，就是它的结构也会设计的像是 autoencoder 那样，会有一个 code 的结构这样。
Well, the structure for the GAN is very different. Okay, for example, you have like here, you have a generator, and you have discriminator. Generator generate fake stuff. Discriminator, you randomly give some fake item generated by the generator, and the real item from the data set. Okay, you randomly give this thing to the discriminator, and the discriminator has to be able to identify it's fake or real. And these two are, each of them will be considered like a complete model, and you train them to fight each other. So this one is kind of like a bad guy. He's trying to create fake stuff. This one is kind of like a police. He's trying to tell the fake from real. And so it's like by competing, having these two models compete each other. So these two models, I mean they are they'll become better and better. Both will become better and better. Okay, but the one that is really useful is this generator. Okay, we are going to use this, I mean, to generate some data set. I mean, for the GAN. Okay, most of the application for GAN is we use it as a generative model. Yes. Okay, so but there are a lot of difficulty. To train GAN. Okay, so. Yeah, obviously I don't have time to talk about those things today, but you are more than welcome to check out the second part of this chapter by yourself. If you have any question on that, you are more than welcome to talk to me. Okay, but unfortunately, obviously I cannot. Well, I only have 1 minute. Okay, so any other question? So if no question, remember we have final exam next week, and the final exam, you are allowed to bring in 1-page cheat sheet. I told you guys about that last time, right? Okay. If you don't remember, don't tell me I didn't say that. Okay. So if some student didn't come to here and they didn't know, you can pretend they didn't. I mean they are not your friend. You know. Yeah, just kidding. Yeah, I mean it's up to you. Okay. If they are good friends, I mean you tell them. If they are not, then well. Anyway, any other question? Okay. If no question, I will well see you next week. Okay. I mean, TA will be here to proctor the exam, but I will be around. Okay. Okay. Thank you. Bye.